So this goes back to Unit 4. We're looking at scatter plots and we're looking at regression equations, least squared regression lines, all that fun stuff. Hopefully you can imagine what this what the scatter plot looks like. So anyways, let's kind of figure out what's going on. We are going to figure out, we're predicting winning percentage from attendance. And so we already have a data point that says that we had a 55% winning percentage with attendance of 34,000. All right, so when that's the case, what we're going to do is we're going to plug in to predict what the winning percentage should be for that attendance. So I'm just going to put W hat right here for predicted winning percentage. So 44 plus 0.0003 times our actual attendance was 34,000. Got a family affair going on in here right now.
Sorry, don't mind us.
It's fine. Anyways, we got all this, and we can just multiply that out, and what we end up with is 54.2 when you do that. So the predicted winning percentage is 54.2%. And so now the question is, what is the residual? Well, residual is the actual minus the predicted. So the actual was right here, 55%. The predicted was 54.2. So when we do that, we end up with a 0.8 residual. And so the happy you who answered C got that right. And the happy you who didn't, hopefully at least you are kind of catching where you made your mistake. So that's just as valuable. All right, any questions on that? Okay, before we actually jump into our content for the day, and I'm going to try and do this somewhat quickly as we go through, I did want to show you on the Canvas page how I changed a few things, which hopefully is easier for you. So all of the AP progress checks and other things, they were scattered in all the different units that we have for class, but I just combined them all together under AP progress checks right here at the top. So you can find all of those. And now these are only the things that say like, yes, I did the progress check, and you just say done. So you'll need to go to AP Classroom to actually do that. These right here, okay, so the ones that are indented are the ones that are the assignments. These right here, these are new FRQ practices that I put up for review, meaning when I say for review only, that means you don't need to turn anything in. But if you wanted to go back to Unit 3, and it's a little confusing, this is AP Unit 3, which does not match our Unit 3. So if you have questions about that. But anyways, it'll just have 2 FRQs. You can look through it, make sure you understand those. Your choice if you choose to use those for practice or not. But especially as we get into the next test on Thursday, you might want to look over the AP Unit 4 FRQs, and that's where you could see some FRQs that might be helpful. All right, that's all I wanted to say with that. And now I will jump into the fun new stuff. Okay, here's our situation. Owners of a backyard chicken farm get pretty regular egg production from their chickens. When the weather is mild, the chickens produce 11 eggs per day. When it's cold, they produce only 5 eggs. When it's hot, the chickens produce 9 eggs per day. About half the year is mild on this location, with cold days only accounting for 10% of the total. Find the probability model for daily egg production. No, actually, we don't need that yet. And what I'm going to do, because you guys have enough practice with this, I'm just going to draw this, and I want you guys to create what you think. Anyone can chip in, but I want you guys to create what you think the probability model for this should be. But this is a good probability model, and one thing just to keep in mind is that the order that we put this 5, 9, and 11 does not matter. So the fact that we did 9, 5, and 11 is just fine. Sometimes there's an intuitive way we want to do it, but here I think it's fair. There's only 3 outcomes. All right, so now what you guys can do, we learned how to do this a pretty fast way yesterday. I want you guys to find the expected value for this variable, and I want you to find the standard deviation for this variable. You can just write it on the screen as soon as you've got it. All right, so we've got our expected value and standard deviation. What I want you guys to do is make sure that you have the stuff written down. It's going to be good to know these numbers. I'll write them again, but at the same time, you can keep up with it. And if you forgot how to do this on the calculator, remember, you just make a list of your outcomes, make a list of your probabilities, keeping these pairs aligned as you do that. And then one variable stats, you're going to have a frequency list, which is going to be your probabilities. Okay, if you forgot how to do that, you can feel free to raise your hand or ask a question. We can actually look at that a little more. But anyways, let me erase all this. That's a good looking model. Hopefully you guys have it copied down. And I'm going to move ahead. We're going to look at another scenario. And I'll erase this in a second. When putting the eggs in cartons, the chicken wranglers have good days and bad days. If they break the first egg they package, there's a 65% chance they're going to break another one. But if they don't break that first one, there's only a 30% chance they're going to break an egg. So there's a 25% chance that they'll break the first egg on any given day. Now we're going to create the probability model for this. I want you guys to come up with this. This one will likely take a little bit more time, but I'm going to create a place for that probability model to go, and you guys can work on it. And again, anyone who's got it figured out can add to it whenever you're done. So those are the probabilities, and go ahead and calculate the expected value and standard deviations, but then we're going to go ahead and look at how this was arrived at for anyone who's confused right now. All right, so let's talk about where these numbers came from. Of course, I mean, the last two right here, that's pretty straightforward. Once you have the probability model, you'll let your calculator figure that out for you. But how do we get the probability model? Remember, we have conditional probabilities here. So if they break the first egg, there's a 65% chance they're going to break another one. If they don't break the first one, there's only a 30% chance they'll break an egg. So this is telling us that we need to have a tree diagram. All right, and I don't need to create any extra space. I'll just put it down here. So I'll squeeze some writing in. So we have two outcomes, is that we break the first egg, or we don't break the first egg. So I'll just call that one complement. So if we break the first egg, there's a 25% chance that's going to happen, 0.25. 0.75 probability that we don't break it. Now, after we break the first egg, there's a 65% chance we're going to break another one. I'm going to put 2 here. It doesn't have to be the second egg, but the probability that we break a second egg overall is going to be, in this case, 0.65, which means there's a 0.35 probability that we don't. Oops, yeah, that's 2 complement. All right, I know that I'm squeezing this tree diagram into the corner, so it's a little hard to read it. Now, if we don't break the first egg, which is 75% probability of happening, there's only a 30% chance of breaking, I say 2, but breaking an egg somewhere down the line. There's a 0.7 probability that we don't break any egg at all on that condition. So anyways, so now it's just multiplying through. If we break both eggs, that's going to be the 0.25 times a 0.65. Because that's breaking the first, breaking a second somewhere down the line. And that gets us this 0.1625. If we don't break an egg the first time and don't break an egg down the line, that's 0.75 times 0.7, which gives us this probability. And so the rest of it, you can either calculate those other 2 probabilities or just give it the complement of what we have. And there we go. That's how we end up with the 1. Okay, so conditional probability tree diagrams, that's what we've got. Now we jump into the new question. So how many eggs are produced and safely packaged for selling on any given day? and we're going to find a probability model. I left this writing up here intentionally for just a minute in case anyone's still trying to write it. All right, so let's kind of figure out what's going on. And now I'm going to clear this so we have some space to work. I'm going to run through this part because this is kind of the new information, but you guys are going to help me here in a minute. So we know that we had to repeat the very first probability model. It was 5, 9, or 11, and the probabilities of that was 0.1, 0.4, and 0.5. For the second one, I'm going to call the second model, well, no, yeah, I'll just call this X again. I'll call it Y. Why not? Why not? So probability of Y. So this is going to be random variable Y is how many we break. There was 0, 1, or 2. And of course, those probabilities were 0.525. This is 0.3125, and this is 0.1625. So now what I want you guys to do is, and we'll work on this together, let's figure out what are the outcomes for X minus Y. And what I mean is X represents the number of eggs produced, Y represents the number of eggs we lost by breaking. So what's the outcomes of X minus Y? And I'm not asking for the probabilities right now. I'm just asking, what are the possible outcomes we could have?
5, 9, and 11.
We could have 5, 9, and 11. I'm going to put those in. 5, 9, and 11. Notice I left some gaps. So I go and I gather 5 eggs or 9 eggs or 11 eggs, depending on the day. And on these days, I don't break any of them, which means I end up with 5, 9, or 11 eggs.
4, 8, 10.
There you go. Maybe I break 1 egg on this day, or on this day, or on this day.
3, 7, 9.
Okay, 3, 7, and 9. So I'm going to spread these out a little bit more. And these days are the ones where we go and collect the eggs, but we break 2 of them. So I'm going to move this 4 over just a little. So I didn't give myself a lot of room. We're going to see these probabilities we're going to need some space. But anyways, we'll just work with it. Are there any other possible outcomes according to our situation?
Would that same as like if you had like 11 minus 2 versus 9 minus 1, would that just be the same probability?
9 minus 0. This I'm going to put a star next to because we have 2 ways of getting 9. This is the only one we have multiple avenues for getting the same outcome. So that's a good point. So here, we'll just start at the beginning. To get the probability of 3, and you can probably imagine what's happening, this would be the probability of getting 5 on that particular day and breaking 2 of them. So we just multiply those together. I can do the first few of these. A second. So when you multiply those together, you're going to get 0.01625. So maybe you picked up 5 eggs that day and you didn't break 2 eggs, you only broke 1. So that means that we have 0.1 times 0.3125, 0.03125. These are easy because we're just moving the decimal over 1. And then the other outcome would be you pick up 5 eggs that day and you don't break any of them. So you multiply those together, you get 0.0525. And you can do this for the rest of these, and you guys can fill in the table with some of these values. just be aware that with 9, there are 2 different ways of getting it. You have to add those together. All right, and I'll let you guys fill in the rest of the chart. So for all the probabilities are good so far, and we're getting the last one put in there, so that's good. And when you're doing the probability for 9, you have 2 options, which is 9 is going to be whatever's left over. But the other thing is, like you can see here, we could just find each probability for getting 9. That's going to be 9. Oops, I didn't mean to do that. Okay, that's going to be 9, the probability of 9 times the probability of 0, plus the probability of 11 times the probability of 2. So you could just do 2 different calculations and add them together. Or you could just figure out what the complement is of everything else added up down here. You know, those all added up along with those and figure out what's left over. But in this case, it's actually probably a little easier just to do the 2 probability calculations and add them. So when we add these 2, and that's good, we're going to add 0.21 to 0.08125. So I'm going to just go ahead and write, I'll do it up above. It's 0.29125 combined. And what we want to always check, of course, is does this add up to 100%? I've done that, and I can guarantee you that these do add up to 100%. All right, we've come up with a probability model for these combined random variables. And they're combined, in this case, we subtracted them. So let's find the expected value and standard deviation. Create those lists. You can put in your values. Now I should call this x minus y. So I'll make this change real quick. All right, and add those numbers in whenever you got them. Yeah, that's a good question. That's something that we're going to jump into. I'm going to cover it to a small degree, but yeah, the important thing when you're doing this is that we are assuming that these are independent. And I think it's fair to assume that what we mean is however many eggs the chickens produce, these people are going to be clumsy or not independent of that.
Okay.
So that is a fair assumption.
Okay.
But and I'm glad you asked that question, because that's going to be a consideration that we need to take. Like, are these really independent of each other, or is the outcome of the first random variable going to determine the outcome of the second random variable? Here, I think it's fair to say that it doesn't. And we do have the expected value now. So there we go. And now we're going to summarize this. And I have a table already set up on the next page that shows it, but you can see 8.9625 eggs is what we might expect on any given day with a standard deviation of almost 2. All right, so let's try and summarize all this. I'll get all this out of the way. All right, so again, we called the initial egg production X and the lost eggs Y. And so we were really finding X minus Y, and that's the notation we were already using. So when you look at this, how does subtracting Y from X affect the expected value?
The expected value is 0.6375 lower.
There it is. Perfect. So really, we could just think of it this way. X minus Y equals, so the expected values function exactly the same way as, you know, intuitively we might expect. So if I gave you the expected value of X, oops, I didn't mean to do that, of X minus Y, that's going to equal the expected value of X minus the expected value of Y. And again, in this case, that's 9.6 minus 0.6375. We're just subtracting them, and we end up with the difference. So that works very intuitively. if we were adding these instead, and we will do an example later where we're adding. So if this is the expected value of random variable x plus random variable y, I can just add the expected value of x to the expected value of y. So this is kind of our takeaway on that front. Now, standard deviation. What the heck's going on with that one? And if you read the chapter and you know what's going on, you can feel free to contribute.
You can't add or subtract standard deviations. You only can add or subtract their variances.
Oh my gosh, that's perfectly stated. I know you read the chapter. That's awesome. So hopefully more than one person out there knew the answer to this. So that's exactly what's going on. I mean, if we try and add or subtract or do any kind of calculation between these two, just kind of straightforward calculation, we're not going to be able to find the this number right here. But it does work when we recognize that we're adding the variances. That's why we talked about variances just a little bit yesterday. Variance is just the standard deviation squared. So when we add the variances, we're using this equation. Okay, and so let's actually work through what that is. So my variance, this is my standard deviation of x, standard deviation of y. And we want to find the standard deviation of x minus y. So now if I square this, if I get the variance now of this standard deviation, that's 1.8 squared, 3.24. All right, if I do the variance for y, it's going to be, yeah, that's 0.5565, and it goes on a little bit longer. So I want to add these together, and that's kind of the basic idea. Add the variances, and when I do that, I get 3.7965, and that's the standard, or sorry, that's the variance of x minus y. So to get back to the standard deviation, I just take the square root of both sides. And now I'll just take the square root of that number. And if you guys are following along and doing this as well, you should end up with 1.948, so on. Okay, so we went through this really long process just so we could find these properties. Of course, if you read, you already knew these properties, but now we can kind of really see it in action. So when we are combining standard deviations among different random variables, we're adding variances. And notice what the formula says right here. It's x plus or minus y. We don't care if we're adding random variable x and y or if we're subtracting random variable x and y. In either case, we're always adding the standard deviations. All right. So we'll talk about that more, but is everyone good with kind of the process we went through here so far? Okay. Get rid of all this. Okay, this is also called the Pythagorean theorem of statistics. And you can see why. I'll just square both sides real quick. And this is going to look pretty familiar, I bet. Looks a lot like it. Now, there is going to be an important difference between this and the Pythagorean theorem. Obviously, there are different contexts, though I will say there is a way of proving this geometrically. I don't know how it's done, but I've read there's a geometric way of representing this and showing it with the same proof that you would for Pythagorean theorem. Anyways, we're always adding the variances. And so now the question is, why do we always add the variances? Even though in this example, we were subtracting the random variables. And the takeaway is that the uncertainty around this increases when we add more random variables into the calculation. So the egg production had a variation, and the lost eggs had variation as well. So in the end, there were more outcomes possible. Think about how we went from 3 outcomes in the first, 3 outcomes in the second, but when we combined it, we had 8 different outcomes that were possible. And just that sheer number of possible outcomes means that we're increasing more uncertainty, all the way down from 3 as the lowest outcome to 11 as the highest. So if you just kind of think of like the possibilities increase, so therefore the variation in the data increases. All right. And that's just conceptually the idea. So hopefully you can remember that and understand you never, ever, ever subtract variances. All right, so I had a question, first of all. How many of you did the homework like these problems last night and did a problem like this and went back and checked your work at the back of the book and found that you did it wrong? Did that happen to anyone? Okay. There is a little nuance to this that I didn't think of yesterday when I was assigning this homework. Okay, there is a difference between the standard deviation of 3 times x and 3 times random variable x. Okay, so I'm going to try and say it now, and we'll see it in the very last example today, kind of where this difference is. When I say I have 3 times x, that means I have random variable x1, random variable x2, and random variable x3. Okay, and when I say I'm just rescaling random variable x, that means I can just take this standard deviation of x and multiply it by 3, and we're good. All right, so if I'm rescaling within one random variable, then all I have to do is multiply the standard deviation by whatever the factor was. But if I have multiple random variables, even if it's the same random variable repeated, if I have multiple random variables, I have to approach it by adding the variances together. So I'll give you an example of that real quick. So let me clear this away, and we're just going to look at this problem right here, D. So this is random variable x has these numbers associated with it, and y has that. So it's going to be, if I want to find the mean of x minus 5y, well, it's going to be, for mean, it's pretty straightforward. That's just going to be 80 minus 5 times 12. So there's nothing really special we have to do with the mean. That one works out exactly the way we think intuitively. 80 minus 60 is 20. We're good. But the standard deviation of x minus 5y, what I'm really saying is that it's the standard deviation of x minus 5 times the standard deviation of y, or 5 times event random variable y happening. So it's going to be the standard deviation of y plus the standard deviation of y plus the standard deviation. I'm not necessarily showing this the right way, but so it's all these events happening. So of course this isn't actually the formula we're using. So that's a little bit confusing the way I wrote it. What this is really saying is that I need to figure out the standard deviation of y happening 5 times in a row. So, you know, just kind of looking at this now, to figure out the standard deviation of 5y, it's going to be the variance of y plus the variance of y. And I'm going to do this 5 times. Of course, I don't need to do it 5 times. I could just multiply by 5, right? So dot, 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 or I could just do 5 times the variation of y. And once I have that, I want to take the square root of it. because these are, and the important distinction is that this is y happening 5 different times. So I have to add the variances. So if I do that real quick, what's the square root of that? Is that, did everyone get 6.71? Again, well, I didn't. This is 5 times 3 squared, because that's the standard deviation of y. Okay. So if I did that right, it should be 6.71. So now I can come back to this and I can say, okay, the standard deviation of x minus 6.71, which is 5y, the standard deviation of 5y, and standard deviation of x is 12. And there we go. Now we can do that subtraction. Oh, I'm sorry. And this is me being stupid. We always add. See? It's Friday. Can that be my excuse? Or maybe I just don't know what I'm doing. All right. So now I'm thoroughly confused. You're thoroughly confused. It'll make a lot more sense. I don't like these types of questions, to tell you the truth, because this isn't real world type stuff. So we're going to do a practice problem with this one. So sorry if I confused things more than I clarified at all. It'll make sense in a second. That's what I keep telling myself, right? All right. So let's look at an actual problem where this is going to come into play. I gotta. All right, we got a little bit off on the answer, and I'm not sure. It was, but we were really close. It was supposed to be 19.2, so I got a little bit off somehow. So a company selling vegetable seeds in packets of 20 estimates that the mean number of seeds that will grow is 18, with a standard deviation of 1.2 seeds. You buy 5 different seed packets. So we don't want to just multiply. We're not rescaling this random variable. We're repeating this random variable 5 times. So our, and we're interested in the number of bad seeds we might get. So what is the expected amount of bad seeds we're going to get in a package?
$10.
Right, so we have a package of 20, and the ones that will actually grow is 18. So the amount of bad seeds we expect is
2.
2. Oh, I see where you're going with the 10, sorry. Yeah, so that was the answer to the first part. So 2 in any one package, which does mean when we're looking at 5 packages of it, it's just going to really be that expected value times 5 to get the 10. The standard deviation 1.2. So yeah, we'll just show that real quick. Expected value of 5 times x is just going to be expected value of x times 5, which is 5 times 2, which is 10. All right. The standard deviation here, this is where we need to add the variances. So standard deviation of 5 times x is going to be 1.2 squared plus 1.2 squared. Of course, I don't even need to add it up all these times. I'm just going to do 5 times 1.2 squared, and then the square root of that. Right. So we can confirm that we all got the same number there. So remember, these do take on the same variable. And that's important to know if this was an FRQ and they wanted you to write a sentence to that effect. All right, the last bit, what assumptions did we make? And this is what, Sam, you were asking, you brought up earlier. So the assumptions we make here is that when we buy 5 different seed packets, that they're independent. Now, is that a fair assumption in this case?
I mean, yes, but I feel like maybe I don't know, the seeds were probably all packed at the same place. So like you could just get like a bad batch for all of like a big portion of seed packets. So
There you go. Yeah, and I completely agree with you. There is a good chance it's independent, but there's also a possibility that, yeah, they all came, like they're all packaged. There's a big batch of seeds and they put in 20 in each packet and it came from really the same group of plants. So who's to say that they're really independent? They could be not independent in that case, but I think it's fair, at least as a starting point, to say they're independent. Okay, but you had really good reasoning there. Okay, so we're going to look at a few other examples. The last bit we're going to say here is continuous random variables. This is the last part of chapter 16, and we've been looking at discrete random variables, and anything there is whenever we can enumerate the outcomes, meaning I could say, oh, we have these outcomes possible, only those 3 outcomes. But if it's a continuous random variable, then any value in between could also be an outcome. So we can't just make a list and say, here are the 3 possible outcomes. There could be an infinite number of outcomes. So here's some examples: cost of hospital bills, stopping distance for vehicles, and time to run a mile. So we're talking about continuous variables again. When we're working with continuous variables, our process is actually a little simpler. We're not creating probability models. We're working with normal models. And if we have the mean and standard deviation for the model and the distribution is approximately normal, that's all we need, and we can now approach it. And we're going to look at a few examples of this. We're going back to chapter 6, but we've kind of been looking at that to some degree anyway. Okay, I'm going to skip over this one. We're going to look at this problem right here. So we're going to assume that we can work with our with this model right here. A casino knows that, so it's all about slot machines and the jackpots. We've got an average payout is 92 cents, but there's a standard deviation of $120. So, I mean, the first question, why would the standard deviation be large on a slot machine?
Because you can lose money or win money.
You can lose money and win money. Where will most of those values be?
Negative range and positive range.
Yeah,
Like
so
around 0.
exactly. And truthfully, the way that you'd model this is with what we call power distribution. So you're going to have a lot of values down here, and I'm putting it in negative because most people are going to lose money, right? But, or most of the time, people are going to lose money. But you could have small payouts. You could have a really big jackpot over here. So this is what we call a power law, power distribution. We're going to talk about that down the line. All right. So anyways, we're still going to work with these numbers. So if you play 5 times, what's the mean and standard deviation of the casino's profit? So let's first of all figure out what's our random variable here is casino's profit. So casino profit, not cast, man. My spelling's gotten worse and worse. Casino profit. What is the profit on any one game? I guess I should say on average.
0.08 cents.
Yeah, 8 cents. So it's kind of hidden in there, but it costs $1. The payout is 92 cents. So the profit, the expected value is going to be 0.08. The standard deviation, of course, we haven't done anything here, so to that is going to be 120. All right, so now we can figure out if we play 5 times, what's the expected value going to be?
$0.40.
There it is, 40 cents. We're just taking this, multiplying this 0.08 times 5 to get 40 cents. All right, what about the standard deviation, sorry. What do we need to do?
I have the answer. Can I just say it?
Yeah, go ahead, tell me the answer.
$268.33.
Okay, so there's the answer, and that's right. And just to show what happened here, we're adding the variances. So it's standard deviation squared of x times 5, because there's 5 times it was played, and then the square root of that total. So you plug that 120 in, you do get 268.33. And now it's good to know that you can just multiply by 5, because the next one, if you added up all the variances like 5 times, that's kind of annoying, and it would be downright, wasting so much time trying to do it 1,000 times. So if it was played 1,000 times a day, we're doing the same thing, but now it's going to be the expected value of 1,000 times and the standard deviation of 1,000 times. So again, same idea. We just multiply that, and what is our expected value going to be?
$80.
There it is. 8 cents times 1,000 is 80. And yeah, now we're doing, just to summarize this up, now it's going to be 1,000 times the variance of this. So the standard deviation of x squared, there it is. Okay, and of course you guys can figure that out, and as soon as you know it, you can either write it down or just shout it out.
$3,794.73.
$3,794.73. So a pretty big standard deviation because of all the potential jackpots and stuff like that, but you're still expected to make $80 per day. Is this profitable for the casino?
Yes.
Yeah, I mean, in the long run, we are still expected to get $80 per day. But I mean, I guess the question really is, some days you'll lose, some days you'll win. It's going to average out to 80. And if that's worth your time, maybe if you only have one slot machine, it's not worth it. But if you had hundreds of slot machines, each making $80 a day, yeah. All right. I wanted to skip ahead to this one right here. Yes, this one right here. We can go back to other examples if you want to see more, but just wanted to run through this one. So we got a bicycle shop. There was a different problem set up in exercise 42. We can go back to that if you want, but they are offering 2 specially priced children's models at a sidewalk sale. the basic model is going to sell for 120 and the deluxe is 150. We can see that basic model is going to have about 5.4 bikes on average sold, standard deviation 1.2, 3.2 average sales of the deluxe bike with standard deviation of 0.8. The cost of setting up a sidewalk sale is $200. Define random variables and use them to express the bicycle shop's net income. All right. So there's a lot going on in this problem. And we start off with the number of bikes we're selling, but really we want these to represent the revenue that they're going to get from selling the bikes. So I'll go ahead and start us off and say that X and Y here is going to be revenue from basic bike, and then Y is going to be revenue from deluxe bike. So it's not going to be as simple as saying, oh, it's 5.4 and 3.2 with standard deviations of 1.2 and 0.8. We want to rescale this. And this is where I was talking at the beginning. You got it maybe a little bit muddy, but hopefully this clarifies it a bit. I want to rescale these variables. So instead of the expected value for X being 5.4 bikes sold, I want this to be in terms of revenue. So what do I do with this?
Multiply it by the cost.
There you go. It costs 120. So the expected value of X is really $648. All right. The expected value of Y is going to be that 3.2 expected bikes sold times that cost. So we'll just do these two real quick. It's kind of the simple calculation. 3.2 times 150 is going to be 480. Now I said that those are the simple calculations, but because we're simply rescaling, we're going from number of bikes sold to revenue from the bikes sold. Now my standard deviation is just going to do the same thing. All right, and this is what we were talking about yesterday. So 1.2 is a standard deviation. I don't have multiple random variables happening. So I'm not adding variances. I'm just rescaling by multiplying by 120. All right, so is that distinction clear? I hope so. Okay. All right, I should have put that as subscript X and Y for the standard deviation, but not a big deal. Now we'll just do the same thing here. 0.8 times 150 gives us 120. Okay. So now we want to kind of think through this again and think, what expected income should I get? So with these two random variables, are we adding them or subtracting them together? Yeah.
Add.
Add. All right, we want the revenue from the basic bike and the deluxe bike, which would just be the expected value of the regular bike plus the expected value of the deluxe bike. And now that's a pretty simple calculation. 648 plus 480 gives us our total of 1128. All right. So I'll stop there just to make sure. Does anyone have questions on what we've done so far? the standard deviation of X and Y is going to be, now because we're combining multiple random variables, now we're adding variances. So I want to add the variance of X and the variance of Y. So just plugging those numbers in, I've got 144 squared, 120 squared, and there it is. All right, and shout out your answer when you found it.
$187.45.
There it is. So, is there anything else we need to do for this problem?
Find your profit.
Find the profit. Okay, so what do we do to find the profit?
Subtract your expected value by the cost of setting up the sidewalk.
There it is. It's the $200 cost of setting it up. Yeah, like you said, only the expected value gets that subtracted away. So there we go. $928 is the expected value for this sale with a standard deviation of 187.45. So it looks like it's going to be profitable no matter what. Okay, and we just defined our variables. We've answered this one. Of course, you might want to write a sentence. Well, you would want to write a sentence if it was FRQ. You would say the expected value or the mean of the net income is $928. Standard, anyways, you know. Do you need to make any assumptions in calculating the mean? How about the standard deviation?
Probably need to assume that the sales of the deluxe bike don't affect the sales of the regular bike.
Perfect. We need to assume they're independent, and just like you said, in this context, that means the sales of one don't affect the sales of the other. Maybe a safe assumption, but yeah, you can just note that right here. Okay, and those are the only ones I wanted to go through specifically in class today. But if you guys wanted to see more, we could look at that. Remember, we have 3 more days of learning, and so as you're going through your homework, which is right here, as you're going through your homework, if you find that you have some questions and things aren't making sense, just bring those to me and we can go through them. But that's really all I've got for today. I'm 24 minutes early. So have a wonderful weekend. But like I said, stick around if you have other questions.
Thank you, Mr. Davis. Bye.
Thank you, Mr. Davis.